Hi, I'm Songbin, a second-year PhD student at Post-Tech, South Korea. I'm excited to present our work, SoundBrush. Sound as a brush for visual scene editing. This is joint work with Junsong, Junseok, Yewon, and Professor Oh. Sound-guided visual scene editing is a task of editing visual scenes to reflect the semantics of input sounds. For example, as shown below, given a source image of a castle, the firework banging sound can be used to insert fireworks in the sky of the source image. Sound conveys diverse semantics. It could be object-related, like dog barking, or environmental sound, like footsteps on snow. It can also contain intensity information about the same type of sound. For example, light rain versus heavy rain. Therefore, the goal of this task is to explore the diverse semantics of sound and reflect them into the edited image. There are existing works on this task, but they have several limitations. For example, some methods struggle to insert new sounding objects and can only manipulate the style of the source image using the sound cues. While some other works can insert sounding objects or manipulate the overall scene with sound, they often alter the original structure and style of the source image after editing. Finally, to the best of our knowledge, no method currently uses sound for 3D scene editing, where multi-view consistency is crucial for 3D scene editing. To address these limitations, our key approach in this work is to first construct the dataset for the sound-guided image editing task. Secondly, we propose a sound-guided image editing model trained with our richly generated dataset, which helps overcome existing limitations and demonstrates outstanding sound-guided editing results. Here we first explain the details of dataset construction. We have constructed a dataset for the sound-guided visual scene editing task consisting of before editing images, after editing images, and audio triplet pairs. More specifically, our dataset has two subsets. The first is fully synthetic, where all before and after editing images are synthetically generated. And the second involves real data, where only the before editing images are synthetically generated. Here's the pipeline for constructing the fully synthetic subset. Given a source audio, we extract the category name of the audio, for example, rain here. We then prompt GPT to take this audio category and generate diverse source and target prompts. The source prompt describes the visual scene, such as location, objects, or weather conditions, for example here as sunny city street, while the target prompt describes the same visual scene with the source audio reflected, here a waterlogged city street, which reflects the audio information. Finally, we feed the source and target prompts to the P2P model, which is an image editing model. P2P model first generates the source image using the source prompt, then uses the target prompt to edit this generated source image. This pipeline allows us to build a fully synthetic subset paired with real source audio. The real data involved subset is constructed differently. From a given video dataset, we first extract an image frame and corresponding audio. Then we feed the audio and source audio to the pre-trained sound source localization model to localize the sounding object in the image using the audio. Next, we feed the image frame and the localized mask to the llama impending model to impaint the localized region of the image. As a result, the tractor is removed from the image. Finally, the audio and image extracted from the video, along with the impainted image, are paired to become a one sample of the real data involved subset. In total, we build over 80,000 of samples for training, and we show several examples of the training dataset below. Now let's move on to the model architecture. The high-level idea for this task is as follows. The model takes source image and source audio as inputs and generates an edited image, where the source image is edited with the source audio. Specifically, given the source audio, we first extract audio features using the clap audio encoder. We then design a transformer-based mapping network, which takes learnable tokens along with the extracted audio features as inputs and map them into audio tokens. This mapping network plays a crucial role in converting the audio signal to be compatible with the later image editing model. We then feed the audio tokens into the clip text encoder and finally pass those tokens along with the source image to the latent diffusion model to perform the sound-guided image editing. As mentioned, the mapping network is important for converting the audio tokens to be compatible with the latent diffusion model. The trainable parts of our model are the mapping network and the latent diffusion model, while the clap and clip encoders are frozen. There are three training objectives: the reconstruction loss, which measures the loss between the edited image and the ground truth image in the latent diffusion space; the contrastive loss, which measures the similarity between features extracted from the audio tokens and image features extracted from the ground truth image using clip embedding space; and the regularization on the audio tokens to encourage the tokens to be more evenly distributed. With these learning objectives and our constructed dataset, we can effectively train our proposed model for the sound-guided image editing task. For evaluation, we use the test split of our constructed dataset, which includes 300 samples. Half of these samples were used to evaluate the sounding object insertion capability of the models, and the other half were used to assess the sound-guided overall scene manipulation capability. These are the metrics we used for validation. The first three are for assessing the editing performance, while the FID evaluates the quality of the edited image. We also conducted human studies for additional validation. Here we first show the qualitative results of our proposed SoundBrush. As demonstrated, given a source image, our model can successfully insert a sounding object or manipulate the overall scene to match the input sound. For example, given the source image of a pyramid, we can insert a lion with the sound of lion roaring, or we can insert a helicopter into the same scene with the sound of helicopter. Furthermore, with a source image featuring a statue on the right side, we can manipulate the scene to include explosions with fire using volcano explosion sounds. Or we can include splashing water with the sound of water splashing. Here we show a qualitative comparison against existing models, including audio token, GlueGen, and Instruct Any2Pix. We observed that other models often fail editing. For example, in the last row, only our model successfully inserts a tractor into the scene, while GlueGen and Instruct Any2Pix insert a tractor but completely change the original structure of the source image. In the quantitative evaluation, our model outperforms on the first three metrics that are related to assessing editing capability while achieving comparable FID score with Instruct Any2Pix. This supports the effectiveness of our proposed model for sound-guided image editing. The human study aligns with the quantitative evaluations. Given the edited samples, we asked participants 3 questions and asked them to rate from 1 to 5. First question is how well the sound semantics are reflected in the edited images. Secondly, how well the original structure and style are preserved. And finally, the overall editing performance. We observed that our model outperforms all other methods in the human perception evaluation. Our model offers an interesting capability of reflecting different audio intensities during editing. For this task, we varied the volume of the same audio and fed it to our model for editing. For example, by increasing the volume of the footsteps on snow sound. We observed that the railroad begins to be covered with denser snow. Similarly, as the volume of the volcano explosion sound increases, the fire and smoke becomes larger and more dynamic. Finally, we demonstrate the extension of our SoundBrush model to sound-guided 3D scene editing. For this experiment, we integrated our model and Instruct Any2Pix with the Instruct Nerve-to-Nerve pipeline. As shown, when we add the tornado sound, our model successfully edits the 3D scene to appear cloudy, while Instruct Any to Pix fails to do so. Similarly, the skiing sound enables our model to insert snow into the 3D scene. Given that multi-view consistency is crucial for 3D scene editing, these results show that our model successfully edits the scene while preserving the original structure and style. In contrast, the comparative method changes the style and structure, thus failing to effectively edit the 3D scene with sound. In conclusion, we propose SoundBrush for the sound-guided visual scene editing task. Compared to existing work, our proposed SoundBrush can effectively insert sounding objects or manipulate the overall scene with sound cues while maintaining the original structure. Furthermore, SoundBrush can be extended to edit 3D visual scenes using sound conditions. For the training of this task, we constructed a dataset that includes before editing and after editing images, along with audio triplet pairs. We believe that our proposed SoundBrush model can be applied across diverse multimedia domains for media creation and editing using sound, and our dataset will contribute to the community by promoting future research in sound-guided visual scene editing. Please also check our project page for more details and to watch more qualitative results. Thank you for listening.